Hello everybody, this is David. In this video, I'm going to share with you how I went about solving the reading the temperature sensor on the Nexys A7 using the I²C. Now, you can still do this with the Basys 3. You just need the Pmod TMP2, which has the same exact sensor, the ADT7420 on the Pmod. It has the same interface with the SCL and SDA, the two standard wires with I²C. Now, to start out, we need to take a look at the Nexys A7 reference manual. And here is the reference manual for the temperature sensor. It starts in section 12. And you can see the interface between the Arctic 7 and the temperature sensor, the ADT7420. It has the two I²C signals, and then also has a couple other signals that I'm not going to use, but they're available, and they're for over and under temperature indicators and critical over temperature indicators. Now, it goes through and explains the interface. So to communicate with the chip, the I²C master must specify the slave address of hex 4B, and then a flag indicating whether to read or write. So in this case, I'm just going to be reading. I'm not going to be writing to any of the registers. And the reason why is because as soon as you power up the sensor, it has different registers inside of it, and the temperature registers are the MSB. It's a 2 bytes, so 16 bits. The MSB is stored in address 00, and then the LSB is in 01. And if you read, so you can just send a read request right away, and then you'll start receiving the temperature data, and that's what I'm going to do. And it auto increments, so once you read the MSB, the master will send its acknowledgement, and then the LSB will come next. So that's what it's what it talks about in this quick start operation. You can, as soon as it's powered up, without any initial configuration, you can read the MSB and then read the LSB of the temperature. And it tells you right here, the result is shifted to the right 3 bits and multiplied by this. The resulting signed floating point value will be a temperature reading in degrees Celsius. Well, I'm not going to multiply it by that, and I'll talk about that a little bit later. Now I'll take you over to the manual for the sensor itself. So here's the data sheet or the manual for the ADT7420. This is a good place to start to check everything out. There's a lot of things that you need to know in here. I'll take you to a couple of important areas of the manual. Let's see. So this talks about, okay, the ADC resolution. So you get 16 bits, but the lower 3 bits are status bits, and then the most significant bit is a sign bit. And so here in my office, where I'll have the FPGA, I'm not going to have any negative temperatures, so I'm only going to be concerned with 12 bits right here, 12 ADC bits. And it goes and talks about the resolution, temperature conversion time. So after power up, right here, fast temperature conversion time, immediately after power up, it takes 6 milliseconds to get a first temperature conversion inside the sensor. After that, every temperature takes 240 milliseconds to convert. So before trying to read from the temperature sensor, we need to wait at least 6 milliseconds to allow that first temperature conversion after power up. Coming down here, all this power consideration is already taken care of on the Nexys A7 when they built it, so we don't have to worry about that. And then right here, the timing specifications is really important. So the maximum frequency on the SCL line is 400 kilohertz. And so taking in consideration all this stuff, I developed a system where I can use an SCL frequency of 10 kilohertz derived from a 200 kilohertz clock, which is exactly 20 times this, so I can specify different changes and on the SDA line that coincide with the SDL, and I'll show you all that. Here's the more timing diagram. Let's see, pin configurations. We don't really need to worry too much about this. We're just concerned with SCL and SDA line. The power and ground is already taken care of. Performance characteristics. Okay, theory of operation. This is a good read right here to go through. Different modes you can use. Temperature data format. This is where it talks about how the format comes out. So there's actually there's a 16-bit mode and a 13-bit mode. And in a 13-bit mode, the lower 3 bits of the LSB, bit 0 to bit 2, are not part of the temperature conversion result and are flags for T critical, T high, and T low. So I'm going to use the 13-bit mode. And then the most significant bit of that 13-bit is the sign bit for a 2's complement number for negative temperature values, like I talked before. So I'm going to use this 13-bit data mode right here. And it says you're going to end up taking the 12 bits. I'm going to drop the MSB and then dividing by 16, which is the same as what they're talking about multiplying by this value right here. 0.0625 is the same as 1 divided by 16, which is the same as shifting your bits to the right by 4. Is the same effect as dividing by 16. And here's some of the values you can get down here. It talks about the registers right here. Register 00, which the address pointer starts at, is the most significant byte of the temperature, and it auto increments to register 1 to get the LSB of the temperature. And then it talks about right here. So bit 15 is the sign bit. So bits 4 through 8, when you put them together, actually no, this is just the MSB. You get the temperature in the 2's complement format, and then these lower 3 bits are status bits. Here, and then you got different status registers and stuff. Not really concerned about all that. So I want to come down to, this is how you write data to it if you were to configure it, and then right here is the part where you're going to, nope, that's still reading data. So there's a reading data section, and this is a section I'm most concerned about right here. And in particular, this section right here, which I'll go back to my PowerPoint and show you more about that. All right, so here's that timing diagram again. I'm not concerned, I put this line here, I'm not concerned with this top part, because that's if you only want to, if you're going to write to a register address to get some data from that address. But like I said, when you first power on the sensor, the address pointer is pointing at 00, which is the MSB of the temperature. So I'm just going to do this timing diagram down here in my circuitry. And these notes right here are important and tell you what you need to do. So up here we got the SCL clock, which in my circuit's case is 10 kilohertz. And so I created a 20 or a 200 kilohertz clock so that I can divide the SCL clock and end up, because what you have to do is you have to set the value on SDA coinciding with certain areas of the S clock. You can't just use the positive or negative edge of the S clock to change your SDA, because like right here in the beginning it says the start condition at the beginning is defined as a high to low transition on the SDA while SCL remains high. So at this point right here, at this high point of SCL, we need to send, well, SDA is going to start at 1 and we need to send it low. So in order to do that, we need a clock that's a division of the S clock. So in my case, my divided clock is 20 times the SCL clock. So if I want to go into a quarter of this way, then I know that 5 ticks later, then I can set the value of SDA, and it's right in the middle. And then right here you can see, well, they talk about as well as the SDA, for whatever bit you're sending, for whatever bit of information, 1 or 0, it needs to change before the next clock period and remain during the entire high period. So in between, in the center of each low period of the S clock is where I'm going to switch the data to send it. And I'll go through my timing diagram in a minute, so let me just go through this. And then a stop condition is a low to high transition while SCL remains high. At the end of the transmission, we're going to have what's called a no acknowledgement by the master. So basically it's going to set up like this. You're going to do your start. We're going to have a start condition. We're going to send the 7 bits of the address, then a read-write bit, and then we need to release, the master needs to release the SDA line, so it needs to float it or tri-state it so that the sensor can send an acknowledgement signal, which will be a 0. And then right from there, it's going to start sending the MSB, the 8 bits of the MSB data. Then there's an acknowledgement by the master, so the master has to take back control of the SDA line and send a 0 to acknowledge to the slave that it received the MSB. Then for the next clock edge, tri-state it again so that the sensor can send the LSB data, and then the master will hold the line high to end the transmission, and then we'll just repeat that start condition back here at the center of SCL and its high point to do it all over again. And then I created a state machine that's just going to loop and go through and do all this stuff over and over again. So the temperature value separated by a low ACK bit, which is right here from the master, and then the read by write bit is set to, it says A1, which is kind of confusing because they have an A1 up here, which is not really true. So the A and the 1 here should be separated by a space. So you set the read write bit to a 1 to indicate a read back, and then a 0 will be a write. So this is my timing diagram that I created for the master circuitry to follow along with that. So right here, SDA starts at 1, and then I'm going to have, this is where my state machine kicks in. So I'm going to have a power up that's going to wait 10 milliseconds, and then, and where's my pointer? There it is. So then halfway in between the first S clock, I'm going to send SDA low, and then in the middle of the low period, so this is the start condition, and then I'm going to go into sending the slave address and the read write. So the slave address, they said, is 4B, which is 1001011. And then I'm going to send a 1 for this clock cycle to indicate a read from the temperature register. Excuse me. And then as soon as that clock high is over, the master is going to tri-state the SDA bus or SDA signal so that the slave can now transmit on that line. It's going to transmit its acknowledgement signal, which is a 0, and then every clock edge is going to transmit the MSB of the temperature. Then in this point, right after this this high period is over, the master is going to take back control of the SDA and send a 0 to acknowledge that it received the MSB. And then right after this high period, it's going to tri-state it again so that it can receive the LSB, the 8 bits of the LSB from the slave. And then it's going to send its no acknowledgement, which is going to drive the SDA high. And then we go right back over to a start condition. So this just essentially loops. After we have the power up period and wait 10 milliseconds, then this is a state machine that's just going to essentially loop through all of these states. So each clock signal is a state. So I have 0 to 27. So I have 28 different states. And so you can see some information over here. When a Z, the master is receiving data from the slave. The sensor, the I²C address is 4B, and then I just went ahead and made an 8-bit register to include the read bit, and then so that makes that the first 8 bits of information being sent is actually hex 97. And then I talk about the clock down here. So the S clock is actually going to be 10 kilohertz, and then the master input clock is 20 times that, so 200 kilohertz. So I can divide and change these signals in quarter or half sections of the SCL clock. So this is my state transition diagram. So right here, I'm going to start at power up. I'm going to wait 10 milliseconds to allow for a temperature conversion, and then we're going to start. And right here is the first start state, where we'll send the low, we'll do the start condition, and then from state 2 to state 9, we'll get each bit, or we'll send each bit plus the read-write bit of the slave address and the read-write bit. Then we'll tri-state it to receive the acknowledgement from the slave, and then state 11 through 18 will receive the MSB. In this state, the master will send the acknowledgement, a low signal, and then tri-state it again to receive 8 bits of the LSB, and then send the no acknowledgement signal, the high signal, and then we come back to start and do it all over again. So this is how the temperature data breaks up. So you got 8 bits of the MSB, 8 bits of the LSB. You basically just truncate the last 3 bits, which are temperature stata bits, because we're using the 13-bit temperature mode. And then I'm also going to just get rid of the 2's complement sign bit here. So I end up with 12 bits of temperature data. And they say if you take that 12 bits and multiply it by this value, it's the same thing as taking that and dividing it by 16, which is the same thing as taking that and right shifting it by 4. So you'll take all these bits and shift it over into 4, or I can just chop off these last 4 bits, which is what I'm going to do. And so the temperature data is actually bit 6 through bit 0 of the MSB, and then put together, concatenated with the bit 7 of the LSB, and this gives us the 8 bits of our temperature data in degrees Celsius. Okay, one more thing before I go into the code. Here's the block diagram for the system. So I'm taking the 100 megahertz clock from the Nexys and creating a 200 kilohertz generator, and that's what's driving the I²C master, and then that will generate the S clock from this, which is 10 kilohertz, to go to the temperature sensor. The SDA line is the bidirectional line between the master and the slave. And then out of here, I'll take those 8 bits of temperature data that I just talked about in the previous slide, and I'm going to put those in binary onto LEDs. I'm also going to send it to a 7-segment control module that's going to convert those to BCD. And then I'm going to use 4 of the 7-segment displays digits to, this one will be the 10s, this one will be the 1s, this one's just going to be a little square for a degree symbol, and then the letter C right here. So you'll read the temperature in degrees C. Now let me take you over to code. Okay, here's the I²C master module I created to communicate with the temperature sensor on the Nexys A7. And it's going to take in a clock of 200 kilohertz. It's got the reset, and then here's the SDA line, which is bidirectional, so I'm using the in-out right there. And then the output, I have an SDA direction line, which is just used in debugging, which I'll show you in a minute. And then the SCL line, which is the clock, which will be the 10 kilohertz. So I'm going to generate the 10 kilohertz SCL right here, using a counter and a clock reg, just like any other kind of hertz generator. So this is the formula that I needed to figure out and what I need to count up to. So 10 ticks of the 200 kilohertz clock, I'm going to invert the clock reg. It starts off at 1. We're going to switch it, we're going to invert it right here to create a duty cycle, a 10 kilohertz duty cycle. And then I'm going to set that register value to the S clock. So right here, SCL is now 10 kilohertz coming out. And so here's some signal declarations. I'm just going to create a parameter of 8 bits, which is the sensor address plus the read bit. So it's 4B plus 1, which ends up with hex 97. This is the temperature, the MSB of the temperature, 8 bits here, the LSB of the temperature, a register to store those, and then the O bit I call the output bit. So this is what the master will output on the SDA line. It's it's going to output the sensor address plus read, and then also use this bit to output the acknowledgement and then the no acknowledgement at the end. And then here's a counter. I'm using this counter here to synchronize the state machine. And I'll show you that down when I go through the state machine. But here's all the 28 states of the state machine right here. So I have the power up state. I'm going to wait 10 milliseconds. We're going to go into start. We're going to initiate the start condition. I'm going to read I'm going to send the address. So the 7 bits of the address, then the read write bit, then receive an acknowledgement from the slave, read 8 bits of the MSB, the master will send its acknowledgement, read 8 bits of the LSB, and then a no acknowledgement, and then after that we'll just come back right back up to start, initiate another start condition, and it just continues looping through there. Here's the state reg. I'm going to start it off at power up, and then so reset them, reset count to 0. Actually, the reset does not really work correctly, so something needs to be done with that, but you'll see it working. But not if you use the reset, it'll mess it up. So don't really concern yourself with the reset part, but always at the pause edge, 200 kilohertz clock, we're going to increment the counter. And then in the case of the state reg, we're going to transition through the state machine based on the value of the counter. So we're going to start off in power up, and then 2,000 ticks of the 200 kilohertz clock is 10 milliseconds. So after 10 milliseconds, we're going to go to start. And then because I want to send the output bit, which is the SDA line, low during the middle of a high period of the SCL clock, I'm going to wait 5 ticks, send it low to initiate the start condition. Then I'm going to wait 10 ticks, which is a half a period of the SCL clock. Right in the middle of the low period, I'm going to start sending that data that's in this sensor address plus read. So I'm going to start sending the address and the read. So for each bit, we're going to assign the O bit to the 7th bit of the sensor address here. After a full complete, so 20 ticks, we'll go to send the next one, and then send the next one. So I'm sending bit 7654322 or 654321, 0 of the address, which is 7 bits, and then and then we get down to the read write. This is the read write signal here, and then so each one of these will happen in the low period of the S clock, so that the bit can stay stable through the entire high period of the S clock. Okay, and then after that read write bit is set, then I'm going to go to the edge of the clock, just like on the diagram before, right at the pause edge or at the neg edge, and then I'm going to tri-state. And I'll show you down how I deal with the tri-state in a minute, but this is we're going to receive the acknowledgement from the sensor, and we're going to read in the 8 bits of the MSB from the sensor. And so you can see how here the input bit, which you'll see down below, is the information coming from the sensor on the SDA line. So I'm just putting in that bit into each bit of the MSB register. So MSB 7, 6, 5, 4, 3, 2, 1, bit 0. Then in this case, the master needs to send its acknowledgement, which will be the O bit. I'm going to set the O bit here to 0. So that way when we transition into here, the O bit is already 0. So as soon as we get to this state, the output bit on the SDA is 0, sending the acknowledgement from the master to the slave. And then after a full period of the clock, we go back to tri-stating and then allowing the sensor to send the LSB. So each input bit will, for each clock cycle of the SCL, is a bit of LSB. So we'll get the high bit all the way down to the low bit of the LSB. Here I'm going to send set the output bit to 1, so that when we transition into the no acknowledgement from the master, SDA line goes high. And then after 30 ticks, I can take it back and the clock, the SCL will be right before pause edge. I'll send it back to the start, and we do it all over again. Excuse me. So how I take care of the in out the bidirectional signals down here. So I have this SDA direction signal, and so in each of these states that I have here, these are the states where the master is driving the SDA line. So in these states, I'm going to set the SDA direction to 1. And in that case, if SDA right here, the SDA line for the output from the master is based on the SDA direction line, which will only be high during these states when the master needs to send data. And that data will be the O bit. Now in the other states, the slave needs the SDA line to send data back to the master. So in this case, in those other states, the SDA direction line will be 0, and the master will be tri-stating the line with a Z to allow the sensor or the slave to transmit its data. And then that data comes in to the I bit here, the input bit, on the SDA line right here. And so the reason why I'm showing you this in Notepad, why are you talking, phone? Okay, in Notepad is because I'm going to use Icarus Verilog, because I had to do a lot of tweaking, and if you're not familiar with Icarus Verilog, I'll show you about it here in a second. But I created a test bench for it. I'm just going to use the clock to drive the 200 kilohertz, and then we have the SDA direction line, and the SCL line that we can look in our waveforms. And it's creating a test bench for Icarus Verilog is the same as doing it in Vivado, except you need to put this initial block in here. You need to specify a dump file to dump all your variables to, so that the waveform generator, in this case I'm using GTK wave, will have those variables to produce the waveform, so you can check the simulation of your device under test, which I didn't give it a name here, but it still worked. So let me show you about Icarus Verilog, and then I'll run the simulation. So if you never use Icarus Verilog, it's a Verilog simulator. Here's the website for it, and it's kind of hard to see, but here's a little link down here where you can get to the installation instructions. And then also when you go to notable links, this is where you can get GTK Wave, which is the preferred waveform generator to use with Icarus Verilog. And the reason why I use Icarus Verilog in this case is because there's a lot of overage that you don't need in Vivado. This is very simple. You run a few commands from your command line. You open your GTK Wave and you check your signals. And if you have to tweak something real quick, you just close that out, go to your file, make a change, go back to your command line, just use your history, type in the commands, and boom, it's a fast way to simulate your modules. And I'll show you the simulation here right now. Okay, so this capture program I'm using is not allowing me to show you this, but I got a screenshot of it here. So I have my two Verilog modules. I got the module and the test bench. And so to use Icarus Verilog, you type this command in here, iverilog-o, give this a name that you'll use for this VVP command, then the modules that you're testing. So this is the actual module under test in the test bench. Then if you have any errors or anything, you'll see that. If nothing happens, then you can go ahead and VVP the I²C master, and then it'll tell you when the simulation is done that your dump file is open for output, and that's the name of the dump file I put right here. And so then I type in the command GTK wave, and then the name of the value change dump file, and then it'll open up GTK wave. Now let me show you GTK wave. After running those commands on the command line, GTK wave will pop up. You expand the window out and it'll look like this. Well, you'll have to click on this plus over here on the top left, expose the device under test, and here are all the signals in that device. So we want to select some signals to view in the waveform viewer. I want the S clock, STA. Alright, I want all these signals. These other signals, the I bit, the MSB, LSB, we're not getting any data from a device, so there's no need to take a look at any of those. And I'll just hit append, and it'll put all the signals over here in the waves window. And now I can go through and change the color format really quickly so that we can better differentiate the signals we're looking at. I'll go ahead and bring that into view. You can see the loop going through the state machine. I'll zoom in a minute. Let me finish coloring this. We'll shoot. I also want to make this into decimal where you can see the counter. Because in the state machine, you notice the 12-bit counter I used decimal values. So now I can track what's happening in here by decimal value of the counter. The O-bit, we're going to keep the same as the SDA. And then I'll just make this purple. Okay, so now we can go through and check the state machine and make sure it's working correctly. So for these first 1999 ticks or 2000 ticks to 1999, we are in state 0. We're waiting that 10 milliseconds, and then we're going to switch to state 1, which is the start. And here's the SEL clock at the top in red. We can see right in the center, we're going to take the O-bit and bring it low, which will bring the SDA low, because at this point the master is controlling the SDA. And this is the start condition, right in the middle of when S clock is high. Let me come back this way a little bit. We can still see the counter values. Cool. So right here's the start condition, state 1. Then we go into state 2 where we start sending the address. So the address bit will be stable. Any bits we send to the device need to be stable for the entire high period of the S clock. And doing this in the center of the low points ensures that we can do that. So right here we start sending the address. This is 1001 for the 9 in the hex 97. And then we're sending 0, 0 or 1, 1, 1, and right after we send that final 1 at the neg edge of our S clock, the master is going to give up the SDA line. It's going to Z it out. So you can see how right here the value, this yellow represents the value of Z, and so that tri-states the line and allows the slave to transmit the its information. So right here at this clock, it'll transmit the acknowledge, and then starting in 0B, we'll start collecting whatever data comes in on the I bit, which is not going to show in here, right? It's just a simulation of the master signals. Well, we're going to start grabbing the MSB. So right here we got, let me backtrack to make sure. Yep, right here's the acknowledgement. We're grabbing the MSB. So bit 7, 6, 5, 4, 3, 2, 1, 0. We've just grabbed MSB bit 0. And then the master is going to send the acknowledge bit. So it's going to drive the SDA line low to acknowledge for this clock cycle that it's received the MSB. And then right here is we'll start gathering the LSB. So this bit 7, 6, 5, 4, 3, 2, 1, 0. And right after that, the master is going to send the no acknowledge, which is sending SDA high. So, and you can see right here, SDA dur, the direction of SDA, which is set in the logic in the code, right, is it changes right here. So when SDA direction is 0, we're Zing the line, we're tri-stating it. When SDA direction is 1, the master is driving. So in this case, the master is driving that no acknowledgement bit, and it's holding it all the way till we get to another start right here. The state transitions back to start. We also reset the counter back to 2000, and we can use the same values for the counter going through the state machine again. All right, let me take you over to Vivado. All right, so now here we are in Vivado. You can see the module hierarchy right here. I have that I²C master, that 200 kilohertz clock gen, the 7-segment control, and the top, and then here's the constraints file. I'll go through each of the modules here. So here's just generating the 200 kilohertz. So I got the 100 megahertz coming in from the Nexys A7, and then here's the conversion right here. So I needed to count from 0 to 249, and then toggle the output register, that is the 200 kilohertz signal, which is then inputted into the I²C master, which this is the exact same file that you just saw in my Notepad++, except I'm using the output of the temperature data here. And then I'm also using the MSB and LSB registers, and then a temporary register to buffer it from these, and also swizzle the bits like you saw. I'm going to take that 16 bits of data and just swizzle out 8 bits. Here's all the states you saw again, and all the state transitions, same exact that we just saw and simulated. And then down here is where I create that buffer for the temperature data. So only when the state is in the NOAC state, we've received the MSB and the LSB of the data. So at that point, the MSB and LSB are complete, and I'm going to swizzle those bits 6 down to 0, and then just bit 7 of the LSB, and put it into a temperature, a data register, a temporary or temperature data register at this clock. And then, so the only time during this, we'll after we've grabbed the MSB and LSB, we'll have the temperature data, and then the output wire is assigned this data value right here, and this will be sent out to the 7-segment display and also to the LEDs through the top. So here's the 7-segment control. Got the 100 megahertz temperature data coming from the I²C master. 7 segments out of 8 for each display, and then because the Nexys has 8 digits, I'm going to call this NAN, and then just to turn all those off is the far left ones, and then I'm just using 4 anodes. And then here's a binary to BCD conversion of the temperature data. This is Celsius data. It's never going to be negative, and it's never going to be above 99 here in my office. So I'm just going to break out 10s and 1s of that data. So to get the 10s, I'll take the temperature data and divide it by 10. To get the 1s, I'll take the temperature data and use the modulus by 10, which will give us the remainder after dividing by 10, which will be the 1's value. Here's the parameters for the segment patterns. I've got numbers 0 through 9, and I'm going to use one of the segments with a little square for the degree symbol, and then the far right segment is just going to be the letter C. So we'll have 2 numbers, degrees Celsius. And then just like this is all the stuff to switch between the anodes like I've done before on 7-segment displays. I have an anode select and an anode timer. So I'm going to create a refresh period of 1 millisecond per digit. So 4 milliseconds for the whole thing. We'll switch through, and then right here, based on the anode select, we'll turn on a particular anode with a 0. Oh, this is old notes right here. But yeah, same way I did before. And now in the case of the anode select, when we're selecting a particular anode, so the far right one, I'm just going to send it the value of C for Celsius. The next one to the left is just going to be that square for the degree symbol. And then based on the value of 1s from temperature data that was converted into BCD, we're going to set the number onto the segments, and then based on the 10s value, set the number to the segments. Now the top module just ties them all in together. Got the 100 megahertz clock coming in, the button C for the reset, the bidirectional SDA line to and from the sensor, the serial clock line, the I²C to the sensor, 7 segments, 4 anodes we're using, 4 anodes we're not, and then 8 LEDs of the temperature data. The SDA direction line is coming out, not using it to connect to anything. It was there for debugging. The wire for the 200 kilohertz signal coming from the 200 kilohertz generator into the I²C master. Of course, the S clock itself is a 10 kilohertz signal. And then just tying them all in, here's the data that comes from the I²C master and goes into the 7-segment display. And it's also, that data is also assigned to the LEDs. Here's the constraints file for the Nexys A7. This is a 50T I'm using. Got the clock 100 megahertz, 7 LEDs, button C for the reset, 7 segs, not using the decimal point. These are the 4 anodes I'm using, the 4 anodes that are just going to be turned off. And then there's actually, you saw from the manual, there's actually 4 lines. I'm not using the temperature critical or the high-low temperature signals. I'm just using the serial clock and serial data line with the sensor. I've already programmed this stuff. Well, let me show you it working. Alright, so here's the temperature sensor working on the Nexys A7. You can see I got the LEDs in play. So the LEDs are reading 27. That's 16 plus 8 is 24, plus 3 is 27, and you can see the reading on here. Now, I've checked this out. I put it in front of my air conditioner, and the temperature actually went down. I think maybe if I can put my finger, because the manual actually says that the temperature reads on the surface of the chip, it just went up to 28 degrees Celsius from the body heat of from my finger. Let me see if I can get it to go up anymore. No. But if I let it go, maybe it'll drop back down to 27. But there you can see it's working. So that's how you communicate with the temperature sensor on the Nexys A7 using I²C and Verilog. Thanks for watching.